What's up, everybody? Hello and welcome. I'm Mr. Endris from Mr. Endris Science Brainery, and this is episode 4 of what I've started doing these short videos to kind of help out with teaching NGSS, especially with Earth Science. That's what I'm on right now. And so I've done really 3 episodes so far, and they've been on like the beginning of Earth and how those processes started, like plate tectonics, how it started, and what that has to do with different types of rocks we have, the rock cycle, and then what that has to do with shaping the Earth the way it is. And so what I decided to do today was take kind of a break from that and just a knowledge and talk about what I should have done in the very first place, I guess, is exactly what is NGSS in the big picture, and how does that have to do with what we're teaching in Earth Science in the smaller picture. Because I think that a lot of teachers are feeling very frustrated because they don't know exactly what this NGSS is and what's at the root of it. And so it makes sense to me, by the way, not to look at the smaller details, but to think of it in an overall framework of exactly what it is. And in my opinion, this is my 21st year of teaching, and so I'm not I haven't been here forever, but I'm not a young lad anymore. But I've seen an awful lot of curriculums come and go, an awful lot of things come and go where they say, okay, well, this is the new thing we're doing. This is really going to teach students better than the old way. And a lot of that stuff is just reactionary towards what happened before. Well, that didn't work, so now we're going to react against that, and we have this new thing that's going to happen. And I think that's what NGSS is. And I'm not saying that's a bad thing at all. I think that NGS has they have it right on. But that's what it is. It's kind of reaction against what used to happen. Well, what used to happen is that we would teach. These are the scientific processes. This is how science works. Here's the scientific method. Here's how you read a chart. Here's all this other stuff. And then you'd have a unit on life science, and you'd have a unit on earth science, or you'd have a unit on physical science. And depending on what grade you're in, you might have the whole. But one way or the other, we kind of relegated that scientific processes to one unit. In fact, that's how textbooks were made. So it's not necessarily a teacher's fault that they were doing this. It's that's how the textbook was made. That's how the curriculum came out. And really what should have happened is that should have been incorporated throughout everything, because that's what science is. Science is not these little factoids. Science is not these. Look at all these species. Look at the dichotomous key. Look at how many planets there are. And isn't it interesting that Venus has this atmosphere that's made of carbon dioxide? Those are things that we have discovered using science. So you really need to change the way that you think about science. Science is not interesting factoids, things that we've discovered. Science is how we've come to those theories, right? It is the process itself. And so what I often say to my students is that what science does is it tries to turn the universe into math, because we like math. Math gives us hard answers on things. 2 plus 2, 4. 10 minus 6, 4. And so 2 plus 2 equals 10 minus 6. So we can do a lot of things with math. Okay, but we have so many different variables in the world, in the natural world, that it's hard for us to isolate all those variables and to turn into a math. But that's what we're trying to do. We want cold, hard data. And if you don't have a chart, then it doesn't really mean anything, right? Like if you can't say this is going to happen and it can be peer reviewed and people can reproduce that, then it really doesn't mean anything, because we need solid data. That's what we're doing in science. We're trying to turn the universe into a math. If that helps, use it. If it doesn't, forget I said that. But the point is that those processes is what science is all about. And what NGSS has done is it has written that into the curriculum throughout the whole year. So you are teaching those processes, and as a small part of that is the little factoids. And that's why we have the three-dimensional learning. That's what the engineering science processes is what I'm talking about. The cross-cutting concepts, those are how all these processes permeate through all the sciences. And then you have one section that is the disciplinary core idea. I always forget what it's called. I call it the DCI. The disciplinary core idea, that's the knowledge. And it's just one of those components. But what we really want to do is have students get there for themselves, which I realize, hey, I hear this all the time from people who are over me and from the people on the internet and people who've come out with the framework and everything, that we're going to have students get this, like you're to present this phenomena, and students are going to go, oh my gosh, I love science, and here I can come up with all these different theories because of it. You're eventually going to have to help them get to this DCI and what's happening, and I understand that. But it's that process that we need them to understand. Okay, that being said, there are a couple things that I did with this with my Earth Science, and I'll mention them more as I go throughout the videos. But I've talked about making models was one of my first things that we talked about, was making a model of Earth layers. And so that is an engineering practice. That's something that we do as scientists. We make models because sometimes the world is too big or it's too small, and we can't study that, or again, we can't turn it into a math, right? And so we make some sort of model. Well, students need to know that that's what models are for. They're for studying, they're for replicating the natural world and isolating variables. And there's some very good things about models, or else why would we use them? But there's also some bad things about models. And this one's kind of a hard thing to get across, but you need to have your students understand. These are called limitations. There's some ways that the models are limited in what they can do. Okay, so for instance, if you build the layers model that I mentioned, I think in episode 1, if you're building layers of the Earth, that's great. It helps students visualize what the layers are doing. They're actually are divided by density, and that's terrific. But what is it about that if you really thought that's what the world was like, how could that hurt your understanding? So limitations aren't just how is it different, because students can always come up with a lot of ways. Well, the Earth is bigger. Yes, the Earth is bigger. Okay. Well, the layers are bigger. Okay. How does that limit your understanding? One of the things so what I come up with that is the biggest limitation is there's no heat. We make these layers inside of a cup, okay, and we don't put heat on it, and so that's a limitation because we don't really know how the heat of the Earth affects all those different layers. And so if you really thought this is how the world was, just these layers right on top of the other, you wouldn't get the dynamism of the Earth and how it moves. Okay. Another example I'll give you with Earth Science, and this is where we're going to go next in my videos, is with stream tables. So we use stream tables to represent weather and erosion deposition. Well, a stream table is a model, right? We're going to create a canyon. You can't fit a whole canyon in a classroom. Models are very good for that. What's good about the model? Well, I'm using crushed up rock, and rock is what the surface of Earth is made of. And so I'm really showing what water does to rock. That is a good thing. It's a very positive thing about my model. It's going to help students understand how water affects rocks, what weather and erosion deposition are. They're going to actually be able to see that. Those are good scientific principles. Those things are happening all the time. But how is that model limited? Well, one thing that's limited about it, let me start off with how is it not limited? Or what are not the things I'm talking about when I'm talking about limitations? Because students are going to say things like, well, there's not it's smaller. I always get that one. Well, it's smaller. Yes, I understand it's smaller. That's how we can keep it in our classroom. We're holding up our stream table with books, and the real world's not held up by books. Okay, but how does that affect your learning? How do we understand the world differently because it's not held up by books? Well, in the real world, so here is a limitation. Water comes from more than just one source. So we have a bowl that we put on top, we put a hole in it, and it drips water down. Well, water isn't constantly moving, it doesn't come from just one source, it comes from all over. And so if we thought this is how the real world worked, where water just dripped down from one source, or you just had one cloud or something like that, all the erosion weather would happen in the same spot, and we wouldn't be able to see all of it happen all over the world. Okay, and that's how our model is limited. We only get to see one thing happening with that. Students will often say, well, there's not a tray in the real world. Okay, well, I mean, so how does that limit our understanding? Well, for one thing, because in our model, erosion weathering eventually stop. Because they stop when they hit the bottom of the tray. But in the real world, maybe they just keep on going. Okay, it's limited by time. They'll say, well, in the real world, it happens faster. Okay, but again, press for that understanding. Because in the real world, it happens faster. Yes, but how does that limit our understanding? And then, and so that's when those questions will start coming out, and that's when you can start seeing the differences or the problems with models and why we use models, but how they're also limited. Another scientific concept that I mentioned early on is the fact that we use data to support whatever claim that we're making. Okay, we use as evidence to support that. In fact, you'll often hear people talk about CERs, or claim evidence reasoning, and that's what that means. Is that everything that we think, and I hesitate to say the word believe, but in a way, I mean, we do believe certain things that are happening because we have data to support that. Okay, and so like the theory of plate tectonics. Well, the reason we call it a theory is because, not because it's just like, well, just some theory, but we call it a theory because it is a philosophical thought that we have that says this can incorporate the most data. Okay, so if you look at the history of science, you'll see we have plenty of data out there, and we come up with a unified theory that supports as much of that data as possible. And so scientists, in a way, choose which theory they want, right? Which theory they're going to follow, but it's a choice based on data. And so, for instance, Newton and Newtonian physics, like Newton came up with these laws of how motion works, okay? And so we still teach that in school, but it's incomplete. And scientists have known that for a long time because there are certain data that doesn't fit that description. And so for one thing, this is the most popular one, is like the movement of Mercury. Newton's theory of gravity could not explain why Mercury was moving the way it did. And so it ultimately came to Einstein, who thought of it differently. And if you don't know this, Einstein's theory is not Newton's theory. They are incompatible. They are different things. And so scientists really do kind of choose which one to operate in. Newton's theories are really good for things that happen on Earth, things at a local level, but when you have to start dealing with really, really big things, you have to start using Einstein's theory. Well, which one is right? Well, Einstein's theory is probably the more right. The reason I say probably is because it doesn't explain all of the data. In fact, that's one of the big quests in science right now is the theory of everything, because we've kind of come up with this thing that describes really very small things, which is quantum physics, and we have these things that describe very, very big things, which is Einstein's theory of gravity. But when you put those two things together, which they would have been together if the universe goes back to the Big Bang, right, then these two theories are coming together and they're incompatible. They're incompatible theories. And so Einstein's theory has to be limited in some way, or quantum physics does. But do you see what I'm getting at is that we teach science almost as though it is like cold, hard fact. This is what is happening. When really what we're doing is we're just saying, this is what our data supports. And so my encouragement to you as a teacher, or if you're a student watching this, or just some guy or girl off the street, is stop talking about how this is what is happening, and start saying this is what our data supports, because that's how the world works. The best data, the best scientific experiments that we have done supports this way of thinking. So whenever students challenge, I say they challenge me. I mean, sometimes students really do mean this because they've heard like we didn't land on the moon, right? That was a big one for a long time. Did we really land on the moon? I don't think we really landed on the moon. Well, we don't really need to shut them up. You say yes, we did. Now stop talking. Okay, but okay, you come up with your data and give it to me. I want to hear why you think that. Now, a lot of students will not take that challenge because they just say that because the Earth's flat. They know that's a very popular thing to say. And I have students, I'm sure you do too, that will, the Earth is, they get really upset with me because they keep saying it's Earth flat. And you can't tell, are you joking or not? I really, at some point, it's not a joke anymore. But, okay, what is your evidence, right? How much evidence supports that theory that you're proposing? And so what this does is this gets students to thinking, what is the evidence that I have for that? And sometimes I do have students that come back and tell me the evidence that they have for why we didn't land on the moon. And then I can give them other evidences that support why I think we did land on the moon, okay? And whichever one the most evidence supports, because once you have to revert to name calling or being upset with one another, you're not doing science anymore. And so anyway, that's another thing I want to talk about with how science works is we collect data, we collect evidence to support certain theories or certain scientific principles. Okay, and so plate tectonics is one of those, and plate tectonics is incomplete. We don't know what hotspots are really. We know that most volcanoes happen on plate boundaries. We think we know how those happen, but when it comes to hotspots, we don't know. And so we might need to modify that theory, or we may even just have a completely new theory in 20 years. And so I often tell students that also, like, maybe you're the person who will come up with the next theory. And that doesn't mean anything to the majority of my students, but some students really, really think that and say, hey, that kind of piques my interest in science, right? So maybe I will come up with the next theory. Okay, so those are a couple things that I wanted to mention in this video, was just why we teach the NGSS, what exactly is the science and scientific method, why do we have it, and then I want to talk about models. And so later on in later episodes, as I start introducing new concepts like variables and scientific experiments, I'll start pointing those out also. All right, I hope this helped, and have a wonderful day.